Hey everyone, and welcome to today's Explainer. Have you ever just watched an ice cube melt into a puddle, or wondered how a boiling pot of water just kinda vanishes into thin air? Well, today we're diving into exactly that for our grade 7 learners. We're going to explore how tiny, literally invisible things create the massive, visible changes that we see in matter every single day.
Okay, let's dive into this. Here's our roadmap for today. First, we'll meet the invisible particles. Second, we'll look at solids, liquids, and gases. Third, we're tackling the big heat misconception. Fourth, we'll track ice turning to water, then to steam. And finally, number 5, the cooling challenge.
So, moving right along to Section 1, Meet the Invisible Particles. This is all about how the invisible explains the visible.
To really understand the worlds around us, we have to look way beyond what the human eye can see. We need to zoom in on the hidden building blocks of all matter, and that brings us to the big essential question for today. How can invisible particles explain visible changes in matter? I mean, think about it. How can something you can't even see with a microscope explain why a solid block of ice turns into flowing water? That is the central mystery we are going to solve together today.
To solve that mystery, scientists use what's called the particle model. Basically, this is the scientific concept that all matter is made of tiny particles, specifically atoms and molecules that are in constant motion. So the crucial point here is that absolutely everything around you, the chair you're sitting on, the screen you're looking at, the air you're breathing, even you yourself, it is all entirely made up of these incredibly tiny atoms and molecules.
Building on that, we have what I like to call the golden rules of matter. These are the absolute non-negotiables of physical science. Rule number 1, everything is made of tiny particles. And rule number 2, and I really want you to lock this one into your memory, particles are in constant motion. They literally never ever stop moving. Even in a rock-hard diamond or a freezing cold block of steel, down at that microscopic level, those tiny particles are constantly jittering and moving around. It's a fundamental law of the universe.
Let's move to Section 2 and see how this builds. Solids, liquids, and gases, the 3 states of matter.
Because if everything is made of moving particles, why does a rock feel so different from water, or from the oxygen we breathe? Well, it all comes down to exactly how those particles are moving. And this brilliantly illustrates the exact differences between a solid, a liquid, and a gas. Let's start with a solid. In a solid, the particles are vibrating in fixed positions, and they're tightly packed. Imagine you and your classmates sitting at your desks. You might be fidgeting or vibrating in your seat, but you're stuck in your specific spot, tightly packed in rows. That's a solid. Now for a liquid, the particles are still close together, but they can actually move past each other. This is kind of like when the bell rings and you're all walking through a crowded hallway. You're close to your friends, but you're fluidly moving past one another. Finally, a gas. In a gas, particles move freely with really large spaces between them. Imagine the bell rings for recess and everyone runs out onto a massive open field, just running in all directions with tons of space between you. That is exactly how gas particles behave.
Okay, Section 3, the big heat misconception. What really happens when matter gets hot? All right, it is time to put on our Mythbuster hats. What actually happens to the particles when we add or remove heat? We all know temperature changes matter, right? When things get hot, they often expand, kind of like a hot air balloon inflating. But what is actually happening down at that invisible, microscopic level to those constantly moving atoms and molecules?
Now, what's really interesting about this slide is it tackles a massive myth. There's this idea out there that when you heat something up, the individual particles themselves puff up like little balloons, expanding and getting physically larger. Let me tell you, that is entirely false. No way. The fact is, the particles themselves never change size. An atom of oxygen is the exact same size whether it's freezing cold or boiling hot. What actually changes is their speed and their spacing. When you add heat, you're adding energy. That energy makes the particles move faster, and because they're moving faster, they bounce off each other harder and spread further apart. So an object expands because the empty space between the particles increases, not because the particles actually grew.
Let's jump into Section 4, ice to water to steam, a worked example in action.
With that huge misconception busted, let's zoom back out and apply this to the real world. Step 1, we start with a solid block of ice. The water molecules are tightly packed, just vibrating in fixed positions. They don't have a lot of heat energy. Then, step 2, we leave that ice on the counter, and it absorbs heat from the room. That heat acts like an energy drink for the particles. They start moving faster, breaking out of their rigid rows. Now, they're liquid water. They're still close, but they're sliding and flowing past each other. Finally, step 3, we put that water in a pot on the stove and crank up the heat to a boil. We are pumping massive amounts of energy into the water. The particles move so frantically fast that they completely break away from each other, spreading out with huge amounts of space between them. They become a gas, steam. So remember, the particles didn't get bigger, they just got much faster and spread much further apart.
And that brings us to our final section, Section 5, the cooling challenge. Time to test your particle knowledge.
Now it's your turn. At the particle level, what happens to a gas in a sealed container when it is cooled? Think about what taking away heat actually means. If adding heat is adding energy and speed, well then taking away heat means taking away energy. Picture those wildly fast gas particles bouncing all over a sealed jar. As you put that jar in the freezer, what's going to happen to their speed? What's going to happen to the space between them? I'm going to leave that challenge to you to figure out. Thanks so much for joining me on this explainer. Keep asking questions and keep exploring the amazing science all around you.